had just begun the discussion of this bare category theorem, right. We shall complete the proof of it today. Let us just recall that we had said that set is said to be nowhere dense, that means a closure its interior is empty, okay. And we had also seen the examples of nowhere dense sets in the last class, okay. And we had also seen that if the set is said to be of the first category, okay, if it can be expressed as a countable union of nowhere dense sets, okay, and otherwise it is of second category. Second category means not of first category, okay. So that is the second category, okay. We shall also recall a few things, what exactly is meaning of this, and of course bare category theorem, okay, let me just take the statement once again. The statement simply says that every complete metric space is of second category. Is of second category. Okay, and this is called bare category theorem, or simply sometimes bare theorem. Okay. Now, before going to the proof of this theorem, let us see a couple of things that will follow from saying that a set is nowhere dense, okay, right. For example, by definition it means that a set is nowhere dense if interior of a closure is empty, okay. That means a closure does not contain any interior point. Let me just write, A is nowhere dense. This means by definition this means interior of a closure is empty, okay. This means a closure does not contain any interior point. So which also means that if you take any non-empty open set, okay, then if you take any non-empty open set, then that non-empty open set cannot be a subset of a closure, okay, because if it is a subset of a closure, then that will be also in the interior, so it will contain interior points. So if it means if you take any non-empty open set, then there will be some point in that non-empty open set which is outside a closure, okay, right. So let us just say that is, this is, you can say, if and only if G for every non-empty open set G, every non-empty open set G, what we can say that X minus a closure intersection G will be non-empty, right. Because otherwise what will it will, if this is empty, it will mean that G is inside a closure, okay, and that is not possible because that will mean that a closure contains some interior point, okay, alright. Now if this set is non-empty, remember, is it clear that this is an open set because X minus a closure is open, G is open. So if this is non-empty, it is open set, it means it will contain a ball, it will contain a ball, and that ball is in X minus a closure as well as in G, okay. That means this, what it means that if you take any non-empty open set, it will contain an open ball which is disjoint from A, okay, which is disjoint from A. So A is nowhere dense if and only if, what I want to say is this, if and only if every non-empty open set, contains an open ball, disjoint from A, okay, right. This is something we shall be using fairly often, okay. in this proof. Okay. All right. Then second thing is again an elementary observation, that is, suppose you take any open ball, let us say open ball with center at A and radius r, okay, then of course this open ball is contained in the closed ball with the center at A and radius r, that is trivial. Okay. So this is contained in the closed ball with center at A and radius r. Okay. What I also want to use is the following, that if I take some radius smaller than this, let us say r by 2, okay, then the closed ball with center at A and radius r by 2 is contained in the open ball with center at A and radius r. That is what I want to also use is this fact. Suppose you take the closed ball with center at A and radius r by 2, I mean not necessarily r by 2, any number strictly smaller than r, okay, then that closed ball with center at A and radius r by 2 is contained in the open ball with center at A and radius r. Okay. Alright. Okay. Now with this preparation, let us come to the proof. Okay. So let us start with a complete metric space. So let X be a complete metric space. Then we want to show that it is of a second category, which means that we want to say it is not of a first category, okay, which means what, which means we want to show that it cannot be expressed as a countable union of nowhere dense sets. Okay. X cannot be expressed as a countable union of nowhere dense sets. Okay. What is the meaning of that? It means that if you take any countable family of nowhere dense sets, okay, its union is not X. Okay. Again it means what? It means that if you take any countable family of nowhere dense set, there will exist some point in X which is not in any of those sets, right. This is what we need to prove. Okay. That is what we need to prove in proving this bare category theorem. Is that clear? Okay. So let us say that let An be a countable family of nowhere dense set, countable family of nowhere dense sets. Okay. We want to show the following, we want to show that there exists X in X such that X does not belong to any of the An's, okay, so that X does not belong to N for all N. This is what we want to show. Okay. If we show that, the proof will be complete. Okay. All right. And how are we going to construct proceed that? We shall be using this fact. Okay. For we have seen here that if any set is nowhere dense and if you take an open set, okay, then that open set should contain an open ball which is disjoint from that nowhere dense set that you saw. This is what we will repeatedly use for each of these sets An. Okay. So start with A1. Okay. Start with A1. So A1 is nowhere dense. A1 is nowhere dense and X is open. Okay, let us take the first open set as X. Okay, and X is open, and X is open. Of course, X is non-empty and open. Okay, X is non-empty. We want to start with a non-empty open set, right? Okay. Okay. So from this, what should happen is that so X contains an open ball which is disjoint from. Okay, so therefore X contains an open ball. Okay, suppose I call that open, suppose the center is A1 and radius is R1, so let us say open ball U A1 R1 such that U A1 R1 intersection A1 is empty. Okay, all right. Then I shall use this fact. Okay, I will take a closed ball with this same center but radius smaller than, let us say R1 by 2. Okay, so and let me call that let me call that set F1. Okay, so let F1 be the closed ball with radius A1, sorry, center A1 and radius R1 by 2. Okay, then F1 is contained in that U A1 R1. Okay, so F1 is contained in that. Okay, this is contained in that U A1 R1. Okay, and hence F1 intersection A1 is empty. Okay, F1 also does not intersect. Okay, okay. So therefore F1 intersection A1 is empty. Okay. Now F1 is a closed ball. Okay, and its radius is R1 by 2. So we can say its diameter is less than or equal to R1. Okay, its diameter is less than or equal to R1. So in fact it's equal to R1 but does not matter. Okay, we can say diameter of F1 is less than or equal to R1. Okay, okay. Also what can we say about F1 interior? F1 interior will certainly contain open ball with center at A1 radius R1 by 2. So in particular it will contain A1. Okay, so F1 interior is non-empty. Okay, interior of F1 is non-empty. So I can say, so interior of F1 is non-empty. Okay. Okay. Now if interior of F1 is non-empty, it is a non-empty open set. Okay, interior is always an open set. Okay, now consider the next set A2. Okay, A2 is nowhere dense and this is a non-empty open set. Okay, this is a non-empty open set. Okay, so this will contain an open ball which is disjoint from A2. Okay, which is disjoint from A2. Okay, so since A2 is nowhere dense, interior of F1 contains an open ball suppose I call that center as A2 and radius R2, that is disjoint from A2, okay, such that U A2 R2 intersection A2 is empty. Okay. We can also make one more thing. Okay, suppose this is true, U A2 R2, that what is the thing, that U A2 R2 is contained in this interior of F1. Okay, okay, and its intersection with this A2 is empty. Okay, if I take any radius smaller than R2, okay, but the same center, will that still be true? Right, I can assume that I can make the radius smaller than whatever is this radius R2 and still it will be true. Okay, so what I will do is that I will take R2 to be less than this R1 by 2. Okay, I will take R2 to be less than R1 by 2. Okay, in fact that, okay, so okay, we may assume R2 to be less than or equal to R1 by 2. Okay, okay, then we do whatever we did here. Okay, I will choose the next set F2 as the closed ball with center at A2 and radius R2. Okay, not R2, R2 by 2. Okay, because we R2 by 2 because we want that to be contained in this, okay. So that is contained in U A2 R2, okay. So what is the property of this F2 now? F2 intersection A2 is empty, okay. F2 intersection A2 is empty. So F2 intersection A2 is empty, okay. Second thing is F2 is contained in UA2 R2, okay. F2 is contained and UA2 R2 is contained in interior of F1, okay. So this is contained in interior of F1, okay. So in particular we can say that F2 is contained in F1, okay. F2 is contained in F1 and further diameter of F2 is less than or equal to R2 and R2 is less than or equal to R1 by 2, okay. Okay, all right. Now what is to be done after that is clear, okay. You proceed in the same way, okay. Next you consider interior of F2. Interior of F2 is non-empty, okay. Since interior F2 is non-empty open set, you look at the next set A3, A3 is nowhere dense, so interior of F2 will contain an open ball which is disjoint from A3. Similarly you adjust the radius, okay. Take the radius, let us say that open ball is, let us say A3 R3, okay. Take R3 to be less than or equal to R2 by 2, okay, and consider the next set F3 which will be BA3 R3 by 2, okay. Suppose you do that, what are the properties that F3 you will get? F3 will be contained in F2, F3 intersection A3 will be empty, okay, and diameter of F3 will be less than or equal to R2 by 2 and hence R1 by 4, okay, R1 by 4, so you can say R1 by 2 to the power 2, okay. So continuing in this way we will get a sequence of closed sets, okay. We will get a sequence of, in fact we will get a decreasing family of closed sets, okay. And what is the property? That each Fn will be contained in Fn minus 1, okay, and Fn intersection An is not empty, okay, and diameter of Fn is less than or equal to R1 by, okay, R1 by 2 to the power n minus 1, okay. So let us just record these things, okay. So proceeding in this manner, we get a sequence Fn of closed sets such that F1 contains F2, F2 contains F3, etc., okay, such that you can say F1 contains F2, etc., etc., Fn contains Fn plus 1, okay, that is first property, okay. Let me write this, okay, this is the first property. Second property is that diameter of Fn is less than or equal to R1 by 2 to the power n minus 1, okay, and third property is Fn intersection An is empty, okay. Now it is clear how to proceed out of this, or in fact why we have constructed this, okay. Now we want to use Cantor's intersection theorem, okay. So what we are saying is that in a complete metric space, if you have a decreasing family of closed sets like this, and if diameter of Fn tends to 0, that is what is happening here, okay. Diameter of Fn is less than or equal to R1 by, that is the reason for adjusting the radius at each stage, okay. So this diameter of Fn tends to 0 as n tends to infinity, okay. So by Cantor's intersection theorem, intersection of Fn will contain exactly one point, okay, right. So okay, by Cantor's intersection theorem, intersection of Fn, n belonging to n, this is contains exactly one point, so this is nothing but singleton x, okay, right, and x is in the intersection of Fn means what? It means x belongs to Fn for all n, okay, so this implies x belongs to Fn for all n, okay, but each Fn is disjoint from An, okay, right, so x cannot belong to any of the Ans, okay, so this implies x does not belong to An for any n, right, okay, and that is what we wanted to show, right, we wanted to show that there exists some x which is not in any of the Ans, right, and that is what we have shown, okay, right. So that completes the proof that every complete metric space is of second category. You can notice that we have made a crucial use of this Cantor's intersection theorem, okay. Using the property of nowhere dense sets, we have constructed a decreasing family of closed sets, okay, such that each Fn is disjoint from An, and hence and also the diameter of Fn goes to 0, and that gives this point x which is in each of the Fn's and hence outside every Fn, okay, alright. Now there is another formulation of this Cantor's theorem, not Cantor's, this Baire category theorem, and that is in terms of open sets, okay. Many books give that version as the Baire category theorem or simply Baire's theorem, and that is as follows, okay. So another version of Baire's theorem, okay, suppose X is a complete metric space, and suppose you take a countable family of open dense sets, okay, suppose you take a countable family of open dense sets, okay, so let Gn be a countable family of open dense sets, that is each Gn is open and each Gn is dense in X, okay. Then what theorem says is this, then intersection Gn is non-empty. In other words, in a complete metric space, countable intersection of open dense sets is non-empty, okay. That is an equivalent formulation of Baire category theorem, alright. Why it is equivalent and how does it follow from this? There is only one very obvious thing to look, you just notice that if Gn is countable and dense, okay, okay, I will just give the proof to you as an exercise, I will just give this as a hint, okay. Show that suppose you take An as x minus Gn, you take An as x minus Gn, then show that An is of first category, okay, sorry, show that An is nowhere dense, okay, show that x minus Gn is nowhere dense, okay, that is the exercise. Let us say you have done this exercise, okay, assume that you have done this, okay, shown that a complement of Gn is nowhere dense, okay, then is it clear that it will immediately now follow from this, because according to this there should exist some point x which is not in any of these Ans, so that must be in the intersection of Gn, okay, that point must be in the intersection of Gn, okay. It is not in any of the Gns, any of the Ans, it means it is in all of the, in each of the Gns. X does not belong to N means x belongs to Gn, okay, and if this happens for each n, x is in the intersection of Gn, okay, okay. Okay, so let us now proceed to next topic, namely, see till now we have thought of various properties of metric spaces by remaining inside only one metric space, okay. That is, we have taken sequences in metric spaces, sets in metric spaces, open sets, closed sets, closure, integers. You can say at each time everything was happening inside one metric space. Now we will take two metric spaces at the same time and consider the functions going from one metric space to the other and consider the limits of such functions, okay. See, till now we have considered limits of sequences, okay. Of course in your calculus course you talk of limits of functions, okay. So we also want to talk limits of functions in that sense, but our functions did not just go from R to R or some subset of R to R itself, but from any metric space to some metric space. Of course in particular both those metric spaces may be real line, okay. So usual concepts of limit will turn out to be special cases of this concept of limit, which we shall be discussing now, okay. So let us now take two metric spaces X, let us say XD and Y, okay, let us say rho are metric spaces, okay. And so we are going to discuss now what is meant by limit of a function. So we should take a function f going from x to y, okay. We should take a function f going from x to y, but as you know, for the consideration of limit, function need not be defined for the whole of x, okay. We can also talk about function going from some subset of x to y. So let us take some subset of x, say let us say a is a subset of x, and of course to avoid triviality let us take a to be non-empty, okay. Okay, and f is a function whose domain is a and codomain is y. F is a function whose domain is a and codomain is y, okay. Alright. We want to say what is meant by saying that limit of fx as x goes to some point is equal to some point in y, okay. Now that point, suppose I call that point let us say the point P, okay. Suppose I want to say what is meant by saying this limit of fx as x tends to P is equal to L, okay. What is the meaning of this symbol, okay, that is what we want to say. So first of all, in order to be able to talk about this, there should be something true about this point P, okay? Something true about this point P. P did not belong to A, okay? That means f did not be defined at that point P, but what we require is that f must be defined on every neighborhood of P, okay. That is, if you take any open set containing P, then that should contain some point from A, okay. And if P is itself not in A, then it means that P must be a limit point of A, okay. P must be a limit point of A. So that is the requirement. So P is a limit point of A, okay. Of course this L must be a point in Y, okay. This L must be a point in Y, okay. Okay. And so we talk about what is meant by saying that limit of fx as x tends to this limit point P is this point L from Y, okay. Again the idea is basically the same, okay. That is, it means that whenever x goes arbitrarily close to P, fx should go close to L, okay. And that is what we will make precise by using this concept of these two distances, okay. That means fx goes close to L means what? That means distance between fx and L must be less than epsilon, okay. And x goes close to P means what? It means distance between x and P must be less than some arbitrarily small number, which we will call delta, okay. So this symbol means that limit of fx as x tends to P is equal to L. This means for every epsilon bigger than 0 there exists delta bigger than 0 such that for all x in x with distance between x and p less than delta, distance between x and p less than delta, this implies the distance between fx and L is less than epsilon, but in y the distance is rho, so rho fx and L less than epsilon. Okay. Okay. We also say that either this symbol limit of fx as x tends to p, or this is also expressed as saying that fx tends to L as x tends to p. Okay. Fx tends to L as x tends to p. Okay. Of course, such a limit may or may not exist. So our next objective will be to decide, given a function, how does one know whether a limit exists or not. Of course, if the limit exists at this point, we will have to just prove that given any epsilon, you have to find out delta depending on that epsilon, such that whenever distance between x and p is less than delta, distance between fx and L is less than epsilon. Okay. Since you would have done lots of such things in your calculus, undergraduate calculus course with real world functions, we shall not go into that kind of examples here. Okay. We should not spend too much time on that. Let us also discuss the other question, how does one show that the limit does not exist. Okay. Again, if you go by this definition, you will have to say that since limit exists means something happens for every epsilon, so limit does not exist means for some epsilon these things do not happen. Okay. That means we can say there exists some epsilon, let us say, let us call it epsilon 0, such that what should not happen, that for that epsilon 0 there is no delta satisfying this. That means whatever delta you take, you can always find some x such that distance between x and p is less than delta, but that is bigger than or equal to epsilon 0. Okay, right. That can be done. Okay, that can be done, but usually that is quite difficult. It can turn out to be quite difficult in several situations. So what we will try to do is that we shall try to find a better way of showing that the limit does not exist. Okay, right, whenever it does not exist. Okay. And to do that, what we shall do is that we shall connect this concept of limit with the one concept of limit which we have already discussed, namely the limit of a sequence. Okay. We want to establish a connection between this idea of a limit of a function and the idea of a limit of a sequence that we have already learned. Okay. Once we do that, then showing that the limit exists or limit does not exist, we can translate all those things in the language of a sequences, and also several theorems about the limits of functions can be translated in the language of sequences, and we can use the theorems which we have already proved about the sequences, and so that many of these things we can quickly dispose of. That is the idea. Okay. So what is the connection? Connection is the following. Okay. This is true, that is limit of fx as x tends to p is equal to L if you take any sequence in x, any sequence in A which converges to p. Okay. Suppose that sequence is xn. Okay. Then fxn should converge to L in y. Okay. Right. That is the connection. Okay. In fact that is what expresses the intuitive idea also clearly, that if x goes close to p, fx should go close to L. Okay. Right. So let us just write that as a theorem. Once that is proved, many things can be said immediately. Okay. So theorem. Okay. So let us say that x, y, a, f, p, etc. are as in here. Okay. That is, I will not write that again. That is x, d, y, rho, a, p, L. All those things are as here. Okay. As are written here. Okay. Then what is the theorem? Theorem says that limit of fx as x tends to p is equal to L if and only if for every sequence xn in A converging to to p, whenever you take any sequence xn converging to p, f xn, okay, let us say converging to p in x, that means d xn p goes to 0, okay, that means d xn p goes to 0, f xn converges to L in Y. Okay. All right. Let us see how this can be proved. Okay, let us look at this way. Okay. Suppose we know that the limit of fx as x tends to p is equal to L, then we should show that for every sequence xn in A converging to p in x, f xn converges to y. Okay. So let us assume this. Okay. So suppose limit of fx as x tends to p is equal to L, and okay, I will simply write this, limit of xn as n tends to infinity is p. Xn is a sequence in A and limit of xn is p. Okay. Then we must show that limit of f xn is same as L. Okay, limit of f xn is same as L. Okay. What does it mean? Okay, let me just write, okay, to show limit of f xn as n tends to infinity is L. By definition, what does it mean? That given any epsilon bigger than 0, we should find out some n0 such that whenever n is bigger than or equal to n0, distance between fxn and L is less than epsilon. Okay. So we start from epsilon. Okay. So let epsilon be bigger than 0. Okay. But since we know that limit of fx as x tends to p is equal to L, for this epsilon there exists some delta. Okay. For this epsilon there exists some delta. So then since limit of fx as x tends to p is equal to L, there exists delta bigger than 0 such that, okay, I will simply write this, that is such that whenever distance between x and p is less than delta, whenever distance between x and p is less than delta, then for that x distance between fx and L, that is rho fx and L, is less than epsilon. Okay. But we also now consider sequence, we also that limit of xn as n tends to infinity is p. Okay, right. So since xn tends to p as n goes to infinity, for this delta bigger than 0 there will exist some n0 such that whenever n is bigger than or equal to n0, distance between xn and p is less than delta. Okay, right. Okay. So we can say that since limit of xn as n tends to infinity is equal to p, we know that whenever this happens, for every epsilon bigger than 0 there exists some n0 etc. Okay, I am using that epsilon, instead of that epsilon I am taking that to be delta. Okay, so there exists n0 in n such that n bigger than or equal to n0 implies distance between xn and p is less than delta. Okay, right. But if distance what we know from here is that for any x, if distance between x and p is less than delta, then the distance between fx and L is less than epsilon. Okay, right. You apply it to that xn. Okay, now we know that distance between xn and p is less than delta, hence distance between fxn and L must be less than epsilon. Okay. So distance between fxn and L must be less than epsilon. Okay. All right. Okay. So that proves one, that is whenever the limit of fx as x tends to p is equal to L, then this implies that if you take any sequence xn in A converging to p, f the sequence f xn must converge to L. Okay. All right. Now let us take the other way. So what does this mean? It means that we know that whenever you are given a sequence xn in A converging to p, f xn converges to L. Okay. And using that we must show that limit of fx as x tends to p is equal to L. Okay. All right. Now suppose that is false. Okay. Suppose that is false. Okay. Then okay, let us say that assume that for every xn in A, for every sequence xn in A converging to p, f xn converges to L. Okay, f xn converges to L. Okay. All right. Now if this is false, if limit of fx as x tends to p equal to L is false, what should happen? As just now, as I have said, there should exist some epsilon 0, okay, epsilon or epsilon 0, whatever you call it, okay. There should exist some epsilon 0, there exists epsilon 0 bigger than 0, such that for every delta bigger than 0, what should happen is that there should exist some x such that distance between that x and this p is less than delta, but the distance between fx and L is bigger than this epsilon 0. Okay. Okay. So there exists delta bigger than for every delta bigger than 0 there exists some x. Of course this x may depend on that delta. Okay. So I shall call it x suffix delta, x delta in A, such that distance between x delta and p is less than delta, and distance between this distance rho fx L is bigger than or equal to epsilon 0. Okay. Now remember, this is true for every delta. Okay. For every delta I can find some x delta such that distance between x delta and p is less than delta, and distance between fx and L is bigger than or equal to epsilon 0. Okay. Now what I will do is I will take this delta as 1 by n. Okay. Take various values of delta. So let delta be equal to 1 by n. Okay. And so for this delta there should exist some x delta. I will denote that x delta as 1 xn. Okay. Let delta be equal to 1 by n and denote this x. Strictly speaking, I should say x suffix 1 by n. Instead of that I will take xn. Okay. And denote x delta to be equal to xn. Okay. Then what should happen? Then distance between xn and p is less than 1 by n. Okay, distance between xn and p is less than 1 by n, and distance between f xn and L is bigger than or equal to epsilon 0. Okay, distance between f xn and L is bigger than or equal to epsilon 0 for every n. Okay. What does this mean? Distance between xn and p is less than 1 by n for every n means what?
xn.
That means xn converges to p. Okay. So this implies that xn converges to p. okay, this implies that xn converges to p, okay, alright. And what does this mean? This means that fxn, distance between fx and L is always bigger than or equal to this number, okay, that so that can never be made arbitrarily small, okay. So fxn does not converge to L, okay. So this means fxn does not converge to L, okay. But our assumption was that whenever xn converges to P, fxn should converge to L, okay. So we have got a contradiction to that, right, okay. So whenever this happens, whenever xn in A converges to P, fxn converges to L, that must imply that limit of fx as x tends to P is equal to L, right. So both these things are equivalent, okay, right. And as I said, what is the advantage of this? Now that we have established the equivalence of these two concepts of limits, okay, limit of a function and a limit of a sequence, of course they are not exactly the same, but you can express one in terms of the other, okay. So the advantage is that in order to prove anything about the limit of a function, I can use the corresponding theorems about the limit of a sequence, okay, and then immediately get the required results here, okay. For example, let me just take one example here, okay, which will immediately follow from whatever we have learned earlier about the sequences, okay. That theorem is that limit of a function, if it exists, is unique, okay. Limit may or may not exist, but the function cannot have two different limits, okay. So we can say that limit of fx as x tends to P, if this limit exists, it is unique, okay. What will be the proof? Suppose limit is not unique, okay, then let us say this limit is L also and M also, and L is different from M, okay. Then what will mean that for every sequence xn converging to P, the sequence fxn will converge to L also and M also, okay. But we have already shown that if a limit of a convergent sequence is unique, okay. So the limit, so if you look at the sequence fxn, if it converges to two different points L and M, those 2 points must be the same, okay, right. So using the corresponding theorem about the limit of sequences, we can prove this theorem immediately. So there is no need to do anything, any separate work here, okay, alright. There is another use of this theorem, okay, and that is the following, okay. Suppose it so happens that you can find two sequences, say let us say sequence xn and sequence yn, suppose both of them converge to P, okay, and fxn and fyn converge to two different limits, okay, then what will that mean? So that obviously that cannot happen if limit of fx as x tends to P is, if this limit exists, okay, right. So one of the ways of showing that the limit does not exist, in fact I would say the easy way of showing that the limit does not exist, is that you find two sequences xn and yn, okay, both converging to P, but limit of f of xn and limit of f of yn are different, right. That is the easiest way of showing that the limit does not exist, okay. Let us just see one or two examples of this and then we will stop with that, okay. Let us, for example, let us take well known example, suppose fx is the so called step function, okay. Let us say fx is, let us say f goes from R to R, and let us say fx means integral part of x, okay, right. It is the greatest integer not greater than x, okay, integer part of x. I think let us suppose I want limit of fx as x tends to 1, limit of fx as x tends to 1. Best thing to do in this particular case is look at the graph, okay. Suppose you look at the graph, when x goes from 0 to 1 fx is 0, right, when f between 0 and 1 fx is 0, and say after between 1 and 2 it is 1, right, okay. Now what I say is that you look at a sequence, suppose I take a sequence xn as 1 minus 1 by n, suppose I take a sequence xn as 1 minus 1 by n, okay, right. What is f of xn? 1 minus 1 by n will lie somewhere here, okay, for every n 1 minus 1 by n will lie somewhere here. So f of xn is 0, right, okay, f of xn is 0. This tends to 1, right, 1 minus 1 by n tends to 1, okay, and f of xn is 0 for all n, so f of xn tends to 0, right. Okay. Now take yn as 1 plus 1 by n, okay, 1 plus 1 by n also tends to 1, 1 plus 1 by n also tends to 1. What about f of yn? F of yn will be, because 1 plus 1 by n is going to lie this side, so f of yn is 1, okay, right. So xn and yn both converge to 1, but f xn converges to 0, f yn converges to 1, so the limit does not exist, okay, so the limit does not exist, okay. Okay, just we are at this topic, let me give you one exercise, okay. Let us say this time I am taking f going from R2 to R. Take any metric on R2, usual metric or L1 metric, or okay, and suppose I take f of x, let us say x is of the form x1 x2, right, so f of x1 x2, okay. So suppose f of x1 x2 is, let us say, something like this, x1 minus x2 divided by x1 plus x2, okay, alright. Now this is not defined at x equal to 0, but does not matter, it still I can talk of limit of f x1 x2 as let us, I will simply say as x goes to 0, okay. X goes to 0 means x 0 of R2, okay, that means x1 x2 goes to 0 0, okay, one can talk of this, okay. Then you would have seen this kind of problem in your advanced calculus course, right, whether such a, and we know that such a limit does not exist, and you would have seen some argument for this, but now look at, use this theorem and use this theorem to show that this limit does not exist, okay. What will be the way of showing that? You will have to construct two sequences in R2 both going to 0 0, but f of one sequence goes to different limit and f of other sequence goes to different limit, okay. Just do this as an exercise, okay. I will stop with that.